Okay. So I'm going to start um, with where I think this is the conversation really is applying to is the idea of solving systems of equations. That's where matrices are um, really going to be useful for us going forward. Um, and so let's take a system of equations like this 2x plus y equals 7, x plus 3y equals 4, which is a system of two equations, two unknowns. I would bet money that all of you in here, you've done this plenty of times before with enough time and energy, could solve this system of equations in a much easier way than we're going to learn right now. For example, you could take this top equation and solve it for y equals 7 minus 2x, plug it in here, and then this equation would be just in terms of x. You could solve that for x and then come back and solve for y. It would be really easy. Some of you may know another way where you could, like, for example, multiply this bottom equation by, let's say, -2, the goal being to make this coefficient -2x, and then you could add these two equations and they would cancel out. That's called the elimination method. Both of those are really still valid methods, and at times you're going to want to do that. But we're going to discuss, it's going to be more long-winded, but there's an end goal to this, is solving this as a matrix equation. And what a matrix equation would look like, I'm going to take the coefficients of x and y. So I have 2, 1, 1, 3. And now that we know how matrix multiplication works, if I multiplied this by x, y, what would I get? Well, this row times the columns, 2x plus 1y. 2x plus 1y, well, what does that equal? That would equal 7. So that would be the top number here. The bottom row times this is 1x plus 3y equals 4. So this is exactly our system of equations, but now written in a little bit of a different way. And so it kind of in matrix algebra terminology, most of the time for a matrix, you use a capital letter. It doesn't have to be A, but we'll call this capital A for matrix A. Okay, now here's going to be a little twist. I know that this is a matrix, but that's also, we're going to view this as a vector as well. Okay, kind of the dual, and you know, we were writing vectors like kind of like a matrix before. So we're going to view this as a vector, and we're going to call that vector, you may remember, you can boldface it in the book, but it doesn't work with pen or pencil. So we're going to put AX as a vector. And I know this is not my choice. I'm just trying to do what the book does. If it were me, I would call this something completely different, like V or something, because you don't want to confuse X bar is not X itself. It's both of them. It's X and Y. That's what they mean by this. 7, 4, we could think of that as another vector, which we'll call, let's say we call it B. I'll use lowercase b. I don't know why. You could use uppercase B as well. All right. And every time we have a system of equations like this, it's always going to boil down in matrix form. It's going to be A times X equals B. A matrix A times a vector X equals another vector B. Now, to solve that, here's the idea. And it was kind of funny. I pre-wrote these notes earlier this morning, but she used the exact same algebra equation that I came up with here. Here's the idea. And I'm going to show you here how we do it with numbers first, and then show you how it looks with matrices. Because the obvious thing to be, if my goal is to solve for X bar, X vector, which stands for X and Y, that's always what I want. I want the answers for X and Y. The easiest thing it would seem to make sense is just divide both sides by A. If I want to get X bar by itself, just divide by A. But it turns out that for matrices, matrix division is not defined. We know how to add matrices, we know how to multiply matrices, but there is no working definition for dividing matrices. So we're not allowed to divide by A and say X is equal to B over A. That doesn't work. There's no way to work that out with matrices. So here's how we're going to do it instead. And it's easier to see with numbers. If I had the algebra equation 3x equals 6, and I told you you were not allowed to divide by 3, which would be the way we would normally do it, right? I would divide by 3. But if I told you you weren't allowed to divide by 3, what would you do? You can multiply, right? You would multiply 1/3, and then you would do the same thing on the other side, times 6. And 1/3 is the multiplicative inverse of 3. Why? Because if I multiply 1 times 1, 1/3 times 3, that just gives me 1x equals 1/3. I know that's 2, but I'm going to write that as 1/3 times 6. And of course, 1 times x is the same thing as x. So I'd have x equals 1/3 of 6, which is 2, of course. Okay. So it's the same, it looks different, but it's the same idea with matrices. If I get a matrix equation that looks like matrix A times x equals b, and my goal is to get x by itself, and instead of dividing by A, what I'm going to do is multiply by the inverse, right? Yeah, here's the other way to think about it. What is 1/3? 1/3 is the same as 3 to the negative 1, isn't it? And 3 to the negative 1 times 3 gives me 1. So that's what I'm doing. I'm going to multiply both sides by A inverse. And then the same idea is true. In the same way that 3 to the negative 1 times 3, which is 1/3 times 3, just gave me 1, A inverse times A kind of gives me 1, but it's the matrix equivalent of 1. What's the matrix equivalent of 1? What do we call that? The matrix equivalent of 1 is what special matrix? Identity matrix. Yeah, that's the identity matrix, which we usually just denote as I. This is the identity matrix. Equals A inverse times B. And of course, the identity matrix times anything was just like multiplying by 1. So that's just going to disappear. And this is going to be kind of our general solution if we're solving a matrix equation for x, the vector x. It's going to always be A inverse times B. And you can't flip it around. If you go back to our particular problem, right, our matrix A is a 2 by 2 matrix. The inverse is going to be a 2 by 2 matrix as well. B is a 2 by 1 matrix. Here, let me go back up to the top. Remember the whole dimension thing, right? This is 2 by 2, 2 by 1, 2 rows, 1 column, equals a 2 by 1. But when I multiply by A inverse, it does have to be on the left side of B, because if you think about it, if I put it, even though with numbers, it doesn't matter, right? If I did 1/3 times 6 is the same as 6 times 1/3. It matters with matrices. For example, like right here, this would be a 2 by 2 again. We'll talk about how to find the inverse times a 2 by 1, which I can do. But if I did it the other way around, right? If I tried to multiply a 2 by 1 times a 2 by 2, I can't do that, right? That's not allowed because the number of columns here doesn't equal the number of rows. So it is important that your inverse goes on the left side. Okay. So this is going to be our solution, but now we need to discuss, you've already discussed this, but let me give you my take on this. How do we find the inverse of the matrix? In order for me to get the solution, I need A inverse. And there's two ways to find the inverse of a matrix. We're going to focus mostly on 2 by 2s here for inverses. There's two ways. One of them is longer than the other. But I really think, and hopefully now after enough tests and quizzes in your class, you're getting the sense that you kind of can't just rely on, a formula. We got to get some understanding and intuition and understand how to find the inverse in this case. Perhaps this is the long way, but we should still be familiar with it because I saw it in both the pre-recorded video for this section and also in class today. I saw her do that this way. So I feel like she's going to want you to know how to do this. To find the inverse of a 2x2 matrix, going back to what we saw up here, A inverse times A, whatever the inverse of matrix A is, when I multiply it together, that should give me I. And so, there we go. We're going to do this, our matrix A, we knew from the top here, I need to go back up. Well, I'll put the numbers in. It was 2, 1, 1, 3. This is matrix A. A inverse is what we're trying to find. We don't know what that is. So I'm going to just put, I'm sorry, I don't like the A1, 1, 2, 1, 1, 3. That gets too confusing for me. So how about I just go A, B, C, D? Okay. I know why we do that. In matrix algebra, they they want to have like the subscripts to identify the row and the column, but it just gets too much for me. So I'm going to use A, B, C, D. And we know I for a 2x2 would be 1, 0, 0, 1. This is another matrix equation, in fact. And there's actually 4 equations here. Here's how we could get that. So here I have a 2x2 times a 2x2. So I know I can multiply these together and get another 2x2. So let's do that. I'm going to make it kind of big here, though. We know this should equal 1, 0, 0, 1. So what goes in my first slot here is my first row times my first column. So that's 2A plus B. Right here is my first row times my second column. That's 1A plus 3B. And then we're at bottom row times the column 2C plus D. And then 1C plus 3D. So there's 4 equations there. Do you see them? There's 4 equations there. One of them is this. If this 2x2 matrix has to equal this 2x2 matrix, then what should 2A plus B equal? If this matrix equals this matrix, that one is in the upper left-hand corner. So 2A plus B better equal 1, huh? This should equal 1. A plus 3B, that's in the upper right corner. That should be equal to 0. 2C plus D, lower left-hand corner, that should be equal to 0. And then C plus 3D equals 1. Is everybody okay of how I'm getting those equations? Okay, I'm seeing some stuff in the chat. Yeah. Probably you were answering as I was going. Remember, this is the inverse right here. This is what I kind of got cut off, but this is what I'm solving for. In order to find the inverse, I need to know what A, B, C, and D are. So I have 2 equations with A and B, 2 equations with C and D. We can solve that. And let's just pick your favorite method here. Doesn't really matter, but how about we take this one? Well, you know what I'm seeing here? This looks a lot easier. if a plus 3b equals 0, doesn't this mean that a equals negative 3b from this equation? And if I plug that into here, let me move this down here. That's going to give me 2 times negative 3b plus b equals 1. That's negative 6b plus b. That's negative 5b equals 1. So I can see that b should equal negative 1/5. I got one of my letters. If I put that right back into here, then a should equal negative 3 times negative 1/5, which is positive 3/5. Okay, so I've got a and b. So take a second now, try to solve these other two equations for c and d. So I solved d equals negative 2. See, this isn't the only way to solve it, obviously. Plugged it into my second equation. That gave me negative 5c equals 1. C equals negative 1/5. And if I just put that right back into here, I can see that d is equal to negative 2 times negative 1/5. D is equal to positive 2/5. So then I have my inverse matrix. My inverse matrix is, remember how it was A, B, C, D. So it's going to be 3/5, negative 1/5. C is also negative 1/5, and then D is 2/5. And one thing you can do with these, I mean, this looks kind of messy, but do you see that I could pull out a 1/5, couldn't I? If I took out a 1/5 from everybody, this would be 3, negative 1, negative 1, 2. Okay, either way, really, this is fine or this is fine. Both of those are the inverse. Perfect. Okay, so that's long-winded. Okay, and she did that in class though, but I really think you should be prepared to know how to do that by hand. Okay, that's really, even though it's longer, it makes sense. If we define our inverse to be the matrix times A that gives us the identity, then this is how it has to be. There's logic behind that. But as you saw in class, there's also a much faster way where, you know, it's a recipe. It's another follow these steps of directions and you'll magically have the inverse, where you really don't get any insight into what's going on. Okay, that's why I think you need to understand this. But there is, of course, the much shorter way to do this using the determinant. And so you saw this in class. Although I'm going to define my matrix to be A, B, C, D, if I have a 2x2 matrix, A, B, C, D, the determinant of A is, you do the product. Okay, terminology here. This is the main diagonal. When you go from top left down, this is the main diagonal right here. You multiply A times D minus the product of the off diagonal this way, B times C. I already put the minus there. Let's make it one big minus. AD minus BC. There we go. Oh boy. That's your determinant. And what the determinant is, it's part of your inverse. the formula for the inverse then becomes this. It's 1 over the determinant of A times, I call this the funny matrix. What we're going to do is take A and D and flip them. So D goes here, your main diagonal entries switch places, and your two off diagonal entries just get a negative. Negative B, negative C. That's our formula for finding the inverse. So for example, did I do that here? Yeah. Let's try it with our matrix that we just worked with. We had a 2, 1, 1, 3. The determinant of our matrix is 2 times 3, the main diagonal product, minus the off diagonal product, 1 times 1, which is 6 minus 1 is 5. And the inverse then is going to be equal to 1 over that number we just got, 1 over 5. And then as we saw, we flip these two, the 2 and the 3 trade places, and the 2 off diagonal entries get a negative. And you can see that is precisely, well, you can't see it, but, well, you can, but I can't see it on my screen. You can see that now that is exactly what we got using the definition of the inverse. Much, much faster, of course, right? So then all that business to find the inverse, let's go back to our problem. Way back when, on the first page of my notes, we were trying to solve this system of equations, 2x plus y equals 7, x plus 3y equals 4. We got to here, we wrote it as a matrix equation, but we have not solved it yet. So let's talk about the solution. So that has the form of ax equals b, and we went through the whole process there, deciding that the answer to this, I'm not going to rewrite all those steps, will always be A inverse times B is going to be our answer. So let's do it. Now remember, X stands for X and Y. So we'll have X, Y equals A inverse. We have that right here. 1/5, 3, -1, -1, 2 times vector B, 7, 4. And you have a couple options. We know with a constant, if you want to, you can put the 1/5 in there, but that might make the rest of the multiplication ugly. I suggest, why don't we just multiply these two, right? This is a 2 by 2 times a 2 by 1. So let's multiply these two matrices together, and then we'll multiply by 1/5. So we have row times column. 21 minus 4 is 17. And then -7 plus 8 is 1. And if I distribute the 5 in, what I get is 17/5 and 1/5. And while it's fine to leave your answer like this is totally fine. Now in matrix notation, we know what that means. What are we really saying? The solution to our system was X equals 17/5, Y equals 1/5, or you could write it as a point, right? X and Y, 17/5, 1/5. You could write it like that as well, either way. All right. Now that we see, there was a little bit of theory there, a little talking about how to find the inverse, but now that we know how to do this, let's solve another system here and we'll see how fast this can be. Just to further mess with you, rather than calling things X and Y and Z, if you had another variable, we're going to call them X1 and X2 now instead of X and Y. Not sure why that we do that, but oh well. Okay, so we want to solve this system of equations. So let's put this in matrix form first. In matrix form, this would be, I have my coefficient matrix, 2, 3, 1, -5, times my two variables, x1 and x2, equals my solution, 5, 9. So this again has the form of a x bar equals b bar as a vector. We know the solution is going to be a inverse times b. But we've got to find a inverse here. So let's go off to the side here. First thing we want is the determinant of A. And the determinant of A, again, is just the product of your main diagonals. So 2 times -5 is -10 minus the product of your off diagonal, 3 times 1, which is 3. So that gives me -13. And then we know A inverse is going to be 1 over my determinant, 1 over -13, times my funny matrix here, where these two flip, main diagonal entries switch places. The off diagonal become negative. I should show you, if one of them is already negative, then if you make it another negative, it would turn positive, right? So you're going to take the opposite of these, whatever it is. It's not that they're always going to be negative. That was only the case because both of these were positive on the last two examples I gave you. Okay, so here's our work for finding the inverse. So now we can proceed here. X bar is A inverse, 1 over -13 times the funny matrix times B. Okay, this shouldn't be too terrible here. I got a 2 by 2 times a 2 by 1. So the row times the column, -25 minus 27. -25 minus 27 is -52. -5 plus 18 is +13. Oh, perfect. And it just so happens 13 goes into 52 4 times. So -113 times -52 gives me 4. And of course, that times 13 gives me -1 would be my answer for X bar, which at this point, let's change that back to what it stands for. It stands for X and Y. Oh, I getcha. I know. Yeah, this unfortunately, this is prime territory for easily missing a negative sign or rewriting numbers too. So yeah, double check your work. I have made so many mistakes on these myself. Luckily, I usually have a bunch of smart students checking my work and catching my mistakes, but not always true when you work on your own. Right. Right. Oh, yeah. I know what's coming next here. So the whole business, again, of finding inverses is to help us to solve equations. Now, of course, we've already acknowledged that there are faster ways, better ways sometimes of solving systems of equations, but this works nonetheless, and we're going to need these ideas for things going forward. Okay, so check this out. Here I have a linear system of equations. In fact, I can go ahead and write that in matrix form. And that's my matrix A here. So we know we're going to need the inverse. So first step in finding the inverse would be finding the determinant of A. And look what happens here. My determinant is 2 times 9, which is 18, minus 3 times 6, which is also 18. So I get a determinant of 0. And what's the problem with that is that if I tried to find A inverse is defined to be 1 over the determinant of A times my funny matrix here, right? I'm not even going to write it, because what would I get? I'd get 1 over 0. And of course, even though we're doing different types of math, you still can't divide by 0, right? This would not be defined. Not defined. Okay. And so what's going on here is the inverse of a matrix doesn't always exist. If the determinant of A is equal to 0, you can clearly see that the inverse is not going to exist. Let's acknowledge that. If A inverse, what I meant to say was if the determinant of A, then A has no inverse. One fancy way of saying that is you could say it's not invertible. A not invertible is another way to say it. Another way of saying this is A is singular. You heard that word today. These are all ways of saying the same thing. Yeah. If the determinant is 0, you could either say A is not invertible, has no inverse, or you could just say A is singular. Now, you know what? I'm going to use this space right here. Let's think about what's happening, though. Let's think about why this is happening. Let me go back to this system of equations. And because fortunately, we're just doing 2 equations, 2 unknowns. These graphically, if I changed x2 to y and x1 as x, both of these are equations of lines. Okay. What's going on here is if I were to graph, I'll put explanation. If I were to graph these 2, I need to fit them on there, don't I? It's not thinking about space here. I guess since I wrote them in terms of x1 and x2, I'll graph them in terms of x1 and x2. X2 is kind of like the y-axis. There we go. When you have lines written like this, my favorite way to graph them is to think about their intercepts. So like you have a x2 intercept of 7/3, that's some number. A x1 intercept of 7/2, that's some number. And that line would look something like this. I don't want to get too much into the detail. Don't worry, you don't have to graph these yet. And what would happen is if you graph this line, found the intercepts, what you would see is these 2 lines are actually parallel lines. I suppose the other way you could do it is if you solve for the slope, like if you think of this as 2x plus 3y equals 7 and solve for y, you're going to get a slope of negative 2/3, I think, for this top one. And if you do the same thing for the second line right here, you're going to also get the same slope. The slope of this line is also negative 2/3, but they don't have the same, they don't go through the same points. So the explanation in this case is the lines are parallel, which means there is no solution to this problem, right? If you were trying to find X and Y values that satisfy both of these equations, you're not going to have any luck. You're never going to find it because there are no points on either line that are on both lines, right? There's no intersection of these two lines. So if the determinant of A equals 0, meaning A has no inverse, one explanation, I'm going to put one explanation, is that the lines are parallel and thus there's no solution. But there is another explanation. Let me do this one. So that all went with that one. This one right here, 1, -4, 2, -8. Notice here, the determinant of my matrix is -8. All right, 1 times -8, be careful, minus, this is -8 as well, but there's already a minus, so minus -8 also gives me 0. Which means I right away know if my determinant is equal to 0, so A is not invertible. I just randomly chose that way to explain it. But what's the reasoning here? Maybe it's easier to see here on this one than the one I did before. What would you get if you took this equation and divided it by 2? If you divide every single thing by 2, that's going to give you x minus 4y equals 3. What's going on here, in fact, is these are actually the same line. It's actually the same line. So I'm going to put not invertible, but in this case, both equations, both are equations of the same line. And if they're both the equations of the same line, then how many solutions do they have? How many solutions can I find that satisfy both of these equations, knowing that they're the same equation? There's an infinite, yeah, exactly. Therefore, there's an infinite number of solutions. So from these last two examples, this is going to be a big idea going forward, actually on Wednesday. I know she's going to use this on Wednesday. From these last two examples, we see that if the determinant equals 0, then of course the inverse doesn't exist. We could say A is not invertible. As a matrix equation, if we're thinking of this in the context of solving a system of equations, it means that the system of equations either has no solution, in other words, the lines are parallel as we saw there, or there's infinite solutions. That's definitely worth Um, reminding yourself of that. This is an important idea in this section. Okay. The other thing, I was watching class today and also watching the pre-recorded videos, very, very high possibility for a quiz or a test question, especially for, well, you'll see in a second here. Now we know how to find the inverse of at least a 2x2 matrix. And so if you were asked, here are two matrices, can you tell me if they're the inverses of each other? Obviously, one way to do it would be to just repeat what we just did, use your formula, find the inverse for matrix A and see if it's matrix B. But what's another way I could show, it didn't say find the inverse of this, it said show that they're inverses of each other. What's the other way I could do this? Go back to the definition. If they are inverses of each other, if A and B are inverses, what should happen is if I multiply A times B, I should get I. Remember, that was the definition of our inverse. And so it probably is even faster, right? If I multiply A times B, 3, 5, 1, 2, times matrix B, 2, -5, -1, 3, I want to see if I end up getting the identity matrix. Yeah, dotted in both. Thank you. That's a very good comment. I remember when we did matrix multiplication. I'm saying it backwards. Matrix multiplication. Gosh, tongue twister. I think I was a little bit ahead, perhaps, but I presented matrix multiplication at one point. I said, doesn't that sound like a dot product? Not sure if she was going to use that language, and I did see her use that today. So yeah, you can explain matrix multiplication as a dot product. You're dotting this row with this column to get this first entry. That's 6 minus 5 is 1. This row times this column to get that entry, -15 plus 15 is 0. Second row, first column, second row dotted with the first column, 2 minus 2 is 0. And then second row, second column, -5 plus 6 is 1. So yes, they are in this case, right? I'm kind of out of time here, but where I could really see this being applied, you can try this one on your own if you want to, but I think I wanted to show you this one. She did show you how to find the determinant of a 3x3 matrix. If you have time, I can show you one, or we could wait till next time. But as you saw, it's a little bit of a process to find the determinant of a 3x3 matrix. And what we still won't do, even though we find the determinant, I don't think we're going to be learning how to find the inverse of a 3x3. So there's really no point for doing this. But where I could really see asking the question if A and B are inverses of each other on a quiz or a test would be, for example, 2 3x3 matrices, because we have not learned, there wouldn't be any way for you to try to find the inverse of this because we haven't talked about it. Okay. So the only way to tell if these two are inverses is to check and see if A times B equals I. That's what you'd want to do. And I'm pretty sure it does. So if you want to run through the multiplication, if you want to check to see, you can do it. If you multiply this matrix by this matrix, I'm pretty sure it does. So maybe that's another good one to try on your own. And if you get stuck, ask me a question later or something, or email me or something. If you have time, and I will answer, there was a question about the worksheet too. But I felt like things are going to be moving pretty quickly here. So, meaning I don't think I'll have a whole lot of extra time on Wednesday as well. Let me show you, let's run through together how to find the determinant of a 3x3 matrix. This is another kind of, it's just a process. If you really want to learn more about why this works, you'd have to take 22B. It's a linear algebra course. But it's definitely harder to find the determinant of a 3x3 matrix. What you want to do, we call this expanding across a row. You can also actually, she didn't show you this, but you can expand down a column. You can do it for any of the rows and any of the columns. But just to make the process simpler so we don't have to remember as much, I think for all of ours in this class, we'll just expand along the top row. So here's how you do it. To find the determinant of A, you're going to go across the first row. You're going to take this first number 2, and you're going to multiply that by the determinant of the 2x2 matrix that you get when you block out the row and the column that 2 is in. So that would be the determinant of 2, 4, 5, 1 of that part of the matrix. And then for reasons, again, you would have to take a linear algebra course to know why this happens. But when you go this, then when you get to this term, you automatically throw in a negative. Minus on the second term. And that second term was 3, and we're going to multiply that by the determinant of the 2x2 matrix that's made up of blocking out the row and column that 3 is in. -1, 4, 0, 1. And then finally, back to plus for this last number, 1 times the determinant block out the row and column for 1, and you get -1, 2, 0, 5. Okay, so it's a whole process here that magically gives us the determinant. I don't think we'll do 4x4s or 5x5s. That just gets too ugly. Okay, so then you usually just do this. You would say, okay, the determinant of this one is going to be 2 times 1 minus 4 times 5. So 2 times, let's say 2 minus 20. This determinant is -1 times 1. So -1 minus 0. And the last one here is -5 minus 0. So this is 2 times -18, so -36 plus 3, and then -5. So I end up with a determinant of -38. And then they ask this question too, is A singular or not singular? Remember, singular means the inverse does not exist. Or in other words, the determinant is 0. Not singular means my determinant is not 0, which means I would actually get a unique solution here. So in this case, since this is not 0, we would say that A is not singular, non-singular. Okay, that was more ambitious than I. Well, I don't know. I don't think I would have cut out anything. There's just a lot of stuff to go through here. All right, I'm going to go ahead and stop the recording.